All right, so my final session is, what is this stuff called dark matter and dark energy? So before I answer that question, I better tell you what dark matter and dark energy are. So I'm going to tell you about our discovery, which led to understanding dark energy, and I'll also explain dark matter along the way. So we remember from Hubble, saw that the universe was expanding. But imagine I want to understand what that means. So an expanding universe means that the separation between two galaxies increases over time. So imagine I measure how fast the universe is expanding right now. That allows me to run the universe in reverse and figure out when the Big Bang was. And that is what I was doing when I met Shude back in 1993 or 4. I had just done my best measurement of how fast is the universe expanding now. This is a much younger me back then. So I had used how fast the universe is expanding to measure how old the universe is, and the number we got was that the universe was about 14 billion years old. It turns out many people were working on that, and the good news is I got the right answer, so that means I get to keep my thesis and my PhD. Now, the problem when we estimated how old the universe would be is that extrapolation, that line is straight. But we know gravity will pull on everything in the universe and slow the expansion of the universe down over time. So if there's a lot of gravity, the universe will take a different path. And for a perfectly reasonable amount of gravity, the age of the universe might be 10 billion years old from my measurements, not 14. And 10 billion was a bad number because we knew that the oldest stars in the universe were at least 12.5 billion years old, just from nuclear physics. And we astronomers are not too fussy, but we do want what is in the universe to be younger, not older than the universe itself. So this sparked the question, why don't we look back in time and see what the universe was doing in the past? By doing that, we could then infer what the universe was going to do in the future. Because if the universe isn't slowing down much, that means it doesn't have much gravity, it doesn't have much stuff, then the universe just gets bigger and bigger over time. On the other hand, if the universe has a lot of stuff, it will expand, slow down, stop, go in reverse, and form what I like to call the Gnab-Gib. That is the Big Bang backwards. So, when I moved to Australia in 1994, I realized we had an opportunity to do this due to new telescopes, new technology, and new ideas. So the idea would be the following. We measure how fast the universe is expanding now, and then we look at progressively more and more distant objects. And if we look back far enough, then I could imagine going through and seeing if the universe was expanding at the same rate in the past as now. So for example, in that case, the universe would just be going along at the same speed. Means it just gets bigger and bigger and bigger over time and goes on forever. It's infinite into the future. On the other hand, if their universe has a lot of mass in it, then if it's above a critical value of how much mass is in it, then the universe is heavy. And if the universe is slowing down faster than this curve, so down here, the universe ends with a Gnab-Gib. It ends in the future. On that side of the line, gravity loses, and the universe keeps going forever. All right, so what did we need? Well, we needed the new 10-meter telescopes, Keck. I've already shown you a picture of Uranus earlier by them. But we also needed something really, really bright we could see on the other side of the universe. And nature gives us this in the form of something we call a type 1a supernova. So imagine two stars are orbiting each other. As the first star puffs up at the end of its life, it can start donating material to the second, smaller star, making it heavier. Eventually, that first star runs out of material and shrinks down to a tiny little star called a white dwarf. That little white dwarf and that other star form a very beautiful thing we call a planetary nebula. But things are still happening. When we come back, that second star, which is now the bigger star, starts running out of its material and puffs up as well. And it can start donating material to the white dwarf, making it heavier and heavier and heavier. And when it reaches the magic number of 1.383 times the mass of our sun, it explodes as a giant thermonuclear bomb, producing most of the iron in the universe. The iron which Australia now exports to China. Thank you very much. So these things are amazing. They are 5 billion times brighter than our sun. They shine for about 20 days before they reach their maximum brightness, and then they fade away into oblivion. But they are so bright that we can track them across the universe. The most distant one we have seen, we have looked back to about 11 billion years in the past with these. But we can measure distances with these, it turns out, very accurately due to my colleagues in Chile who were able to refine how one uses these to measure distances very accurately. So in 1998, a team that I was part of, and there was also a team at Berkeley who we were competing with, came up with essentially the same but surprising answer. When we measure how fast the universe was expanding back in time, and we compared the nearby objects with the distant objects 5 or 6 billion years in the past, you can see they were up above the line. The universe was expanding slower in the past and sped up. Now, when we first measured that, I have to admit, I thought we must have made some sort of error. We checked our work, we checked it again, and then we found out, so essentially as we were writing the paper up, that the other team was getting the same answer, and they were checking their answer and checking it again. And so we sort of arrived to this conclusion at the same time independently. So the universe is speeding up, it's accelerating. What would do that? Einstein came up with an idea. He came up with an idea in 1917 that if space itself was full of energy, under his equations of general relativity, his theory of gravity, the same one that predicts gravitational waves, that this energy would gravitationally push on itself and cause the universe to accelerate. It turns out that this material he put in there as a mistake. He was going to use this to counteract gravity and keep the universe from expanding at all. Later calls that him acting like a donkey was, I believe, the correct quote. So we don't know what this stuff is. We call it dark energy today. When we made this measurement in 1998, people were rightfully so skeptical. So they went and looked at other parts of data. And they said, what are some of the other experiments we can do on the universe? One of those groups was in Australia. And they went out and they mapped galaxies in detail. And I should say that discovery is that work of not just myself, but 20 of us. And here we are in Stockholm all together for the only time we've all been together at one point, because we worked via the internet. But my colleagues in Australia went through and they said, let's go observe the universe and see what it looks like by how the galaxies form. And we're going to compare what the universe looks like compared to what the universe looks like in a computer. So here's the universe they observe, and here are 4 different models of the universe. So what I want you to do is use your computer and figure out which model looks like the data. 1, 2, 3, or 4. And then I'll tell you the right answer when you do the full analysis. All right? So if you said model 1, you're wrong. Model 2, you're wrong. Model 4, you're wrong. Model 3, you're right. Model 3 is an interesting model. It's a model that's made up of something we call dark matter. Dark matter is material that goes right through itself and everything else and only interacts by gravity. The only thing it can feel is gravity. It would be invisible, but otherwise it seems to imply that the universe is roughly 30% this dark matter, or 25% dark matter, and then there's something mysterious missing. But they're not too sure whether or not it's mysterious or not. It really couldn't tell too much more. Now, it turns out those galaxies are formed from what we can see in the very early universe. This is the cosmic microwave background I told you about earlier. And the little bumps and wiggles you see in this image are sound waves. They're sound waves left over from the Big Bang, and they've rippled around at the speed of sound. And it turns out the speed of sound is 57% of the speed of light. We know that very accurately. And we can go through and we can make a prediction of how sound waves travel in the universe. Now, it turns out that what the universe is made out of affects how those waves travel. So think of the universe as a pond, and I plop a rock in it. If it's water or honey, it's different. The Big Bang's like throwing a bunch of gravel into the universe, and so you get this ripple pattern, which you take a picture of 380,000 years later, and then you get to ask yourself, what does that ripple pattern look like? So it turns out that when you do that experiment, you find out that the universe is made out of dark energy, dark matter, and 5% atoms. So pretty much the same answer that we got in 1998. So what is this dark matter? Well, we really don't know, but we have a guess. Imagine there is a universe full of a particle we have not yet discovered, the dark matter particle. That dark matter particle can travel right through the Earth, just like a neutrino. So neutrinos would be sort of a dark matter particle, except where we know there aren't enough of them. So it's got to be something else. Well, we can sort of go out and measure that in nature. This is known as the bullet cluster. And what we can see here is that we can measure where the dark matter is by how gravity distorts space. So we can see that in these bluish areas. And with X-rays, we can see where the atoms are. And we see as these two groups of galaxies collide with each other, all of the atoms get piled up in the center. It's a big train wreck because atoms interact with each other. But the dark matter just goes whoop, right through itself, just like you would expect. Well, okay, that's a good idea, but what really is dark matter? I want to know, is it a particle? How am I going to find out if it's a particle? Well, we can do this. We have the Large Hadron Collider. Imagine that the dark matter particle can be created by crushing atoms into each other. Then occasionally you will make a dark matter particle and it will just travel right through the Earth away. Every time they collide atoms together in the Large Hadron Collider, they track each particle. And what they will see is the collision and then something will suddenly disappear. There will be like something missing. And if you keep on getting the same amount of something missing, you can infer that there's a particle there you didn't know about, the dark matter particle. We have not yet discovered it this way, but that's one way you might. Another way is to go into a mine and put atoms there and hope that dark matter very rarely does interact with atoms. So in this case, we put large amounts of xenon, a very heavy inert gas. We cool it down so it's a liquid. You wait, and when it hits, when a dark matter particle collides with a xenon atom, we expect it to put out a little flash of light, which we can detect. So right now, we've kept hundreds of kilos of xenon underground for a couple years, and we haven't seen anything. So we're still waiting. The hope is to go to a ton of xenon, or maybe even 10 tons of xenon. Most models for dark matter predict you should see something eventually, if their guesses are correct. And finally, the universe is a great laboratory, and when, for example, we look at the center of our galaxy, we see some unexplained gamma rays. It had been hoped that potentially those gamma rays were caused when dark matter particles hit each other and maybe annihilated themselves. That is, it might be that dark matter is its own antiparticle. So it would, when it hit itself, maybe produce a gamma ray. Well, I think the betting money now is that what we're seeing is not due to this, but it's still possible if we keep looking, we will see a similar signature somewhere else in the universe. So there's hope we'll find what dark matter is, but no guarantees. Our worst fear is that dark matter never interacts with atoms in any way, shape, or form, in which case it will always be a bit of a mystery because we're made of atoms. And if it never interacts with us, the only way we're going to detect it is through gravity. And gravity is a very, very weak force, and we can't measure individual atoms or individual particles with gravity. That would be a terrible, terrible thing if it were true. Dark energy, well, it's hard. The only tool we have right now to measure dark energy is the accelerating expansion itself. And so we can ask the question, does dark energy get created exactly as space is created? That's Einstein's idea. Or is it a little different? If it's a little different, it will change the speed of the universe just slightly differently than what Einstein predicts. So we have been working on this since 1998 collectively as a community. This is how many supernovae we have now. Each one of these objects is a measurement, and this was the answer from 1998. It's still exactly right. There are no deviations from Einstein's prediction. But it's not the only way we can do things. We can go through and use these sound waves and know that we can measure them better and better. And when we do that, this is like an oscilloscope of the universe, tells you how many sound waves there are, and that measures things very accurately now too. Again, Einstein, exactly right, still in 2016. Those sound waves eventually become galaxies. And so the sound waves of today end up forming galaxies, and we can look at how big those sound waves are in the universe today. And we have done that using giant surveys of galaxies. This is the Sloan Digital Sky Survey. And that allows you to see the sound waves in the galaxies of today. What answer do we get? Einstein's dark energy, exactly right. every way we look at it, we get the same answer, which is that the universe appears to be 70% dark energy that looks an awful lot like what Einstein predicted, 25% this dark matter that seems to just go right through the Earth, but has gravity, and 5% atoms. The universe is 95% stuff that we do not understand. Yet, we can predict what it's going to do with exquisite accuracy. So that is the funny place that we find ourselves in astronomy today. So what's our future? Well, in case you didn't know it, the sun is getting hotter. This isn't anything to do with global warming. We're doing that ourselves. And in about 500 million years, it's going to boil off our oceans. And in 5 billion years, it's going to cook us completely and destroy the Earth. But as I told you, there are stars that will last for trillions of years, and we're looking for planets around them. So astronomers are out trying to make sure we have a place to go. But the future of the universe seems to be dark energy, because dark energy is part of space itself. The more it speeds the universe up, the more of it there is compared to us. And so it can push harder on the universe, making it expand even faster. So the faster it goes, the faster it wants to go. Eventually, the universe expands so quickly that light traveling from galaxies we can see today will no longer be able to reach us. That is, when a photon tries to go to us, it's going through expanding space and it stalls. It can no longer get through space. Meaning we're going to live, it seems, in a very lonely place in the future. A place where we are it. Now, it turns out we don't understand dark energy. And until we understand dark energy, anything is possible, because a good theorist can make dark energy go away or change. But unless the dark energy disappears very quickly, the universe seems to be bound to expand at an ever-increasing rate, so that it will slowly fade away and die, leaving us alone and cosmologists like me unemployed. Thank you very much.
Thank you, Brian. So, any questions from the audience? Any microphones?
I think we have them all, Shude.
Just a second.
Thank you, Professor. The universe is expanding, and the universe is very large. So my question is it expanding at the same speed everywhere in the universe, and is it expanding at the same speed every direction?
Yep. So that's a very good question. So as near as we can tell, the answer is, to very high accuracy, the universe is expanding everywhere at the current time at the same speed, and in every direction the same. Imagine that the universe was expanding a little different direction, a little bit different in that direction compared to that direction. It turns out, when I look at the cosmic microwave background, that means that part of the universe would be at a different distance than that part, which would mean it would look different. But the cosmic microwave background I showed you has all those lumps and bumps, but it's actually the same to 1 part in 100,000. So those little lumps and bumps are really tiny. So to within a factor of 100,000, 1 part in 100,000, we can show that the universe is expanding in the same way in all directions. It's only if you were to put us in the center of the universe, I don't know what that means, where everything, there's a circle and a sphere around us, which is doing exactly the same thing in all directions, we could be fooled. So imagine I make the universe change in all directions in exactly the same way, and we're right in the center of that. That we couldn't tell. But that would mean we're at the center of the universe, and that sort of goes against our intuition. We should not be a special place in the universe.
Okay.
Okay, thank you, Professor, for the very instructive, inspiring presentation. So you mentioned that the dark matter, some people presume that the black hole is made of the dark matter. Is it possible if we capture the dark matter, then we could have a higher control of space-time to create the black hole or the wormholes? And the second question is, what do you think is the fundamental drive of the expansion of the universe? Thank you.
Okay, so with respect to black holes, you can't tell what's inside of a black hole. That's sort of by definition. What's in a black hole stays in a black hole. So just from a practical point of view, dark matter is very difficult to do anything with because it goes right through everything. So imagine I want to make dark matter change direction. For an atom, I can use a magnet, or I can use, I can use electromagnetics. There's many things I can use. I can use mirrors. I can use forces of nature. Dark matter, I can't. The only thing I can use is gravity. So dark matter is not going to be very useful if we could control it, because we can't. That's by definition of doing anything with black holes. So I would say that if anything, if we were going to make our own black holes, we'd probably want to use atoms, because those we can really control by definition. What is driving the expansion of the universe? Well, we don't really know why the universe is expanding. The reason the universe is expanding now is because it was born in the Big Bang expanding. And if you want to know why the universe was born expanding in the Big Bang, I'm afraid I could make up an answer, but I don't have an answer for you. It just did. And so what we see is the universe getting bigger and bigger. And what is interesting is because the universe is speeding up, the initial Big Bang event is no longer driving the expansion of the universe. It is the dark energy and the gravity of how gravity works with that that's driving it now. So that's a complicated answer, but it's a complicated question, although not maybe completely obvious.
Okay, maybe.
Professor, you mentioned just now that the dark energy creates space while it goes. So why do we make a distinguishment between the dark energy and space? Why don't we view them as one thing?
Well, at some level, if dark energy is truly part of space itself and never ever changes, then you are right. Dark energy is part of the definition of space. But we don't know that yet. What happens if dark energy changes over time? Then it's not part of space. It just inhabits space. So that's one of the big questions, and that's that fundamental question is, what is dark energy? Is it a fundamental property of space? Or is it something like the Higgs field? We all know of the Higgs boson discovery. Well, the reason the Higgs is interesting is it leaves a field behind, energy that's part of space. And it could be that there is some undiscovered particle that would be doing the same thing and creating the dark energy we see. So that would be different than space itself. So that's really the question we're trying to understand.
Okay, Yigong.
So in one of your slides predicting the future, you alluded to the concept of generating more dark energy or dark matter. So are you saying the percentage of dark matter and dark energy is increasing over time?
Yeah, so quite remarkably, in general relativity, as the universe expands, the dark energy in a piece of space stays the same, but the universe, you know, the part of the universe that we can see right now becomes bigger and bigger, so the total amount of dark energy increases. Now you might ask yourself, well, how do you do that? Doesn't that violate the conservation of energy? But general relativity has a very complicated accounting system. What is driving the expansion? Well, the expansion itself, that has some term to it as well. And in a simple analogy, dark energy, and this is for the physics literate, people literate in physics, has negative pressure. And so if I want to think about the work being done in the universe, I have negative pressure trying to change its volume. So that's negative. The creation of dark energy is positive, and they more or less offset each other. Now within general relativity, it's not quite that simple, but that's the basic analogy. You have to think about everything, including the expansion, how much stuff there's in the universe, and it turns out the curvature of the universe is another thing you need to worry about.
Okay.
Just have a question for your data for the acceleration of the universe expansion. I see there's some at low z, a little bit at high z, there's a sort of a
The gap in the middle?
between.
Yeah.
So is there any particular object, or if you have any further far away, or your team or someone are working on it?
Yeah, so if I show you, well, let's go back to the most recent data. I think in the initial data, there was really an issue, and there still is an issue, and it's a technological issue. Down here, we find the supernovae one by one in galaxies with little telescopes. So I can go and look at a galaxy, look at another galaxy, look at another galaxy, and occasionally a supernova goes off and I find them. Out here, I use a great big telescope, and I only have to look at a tiny little piece of sky that has tens of thousands of galaxies in it. So in that way, I can find supernovae because I get to see thousands of galaxies in one picture. So I'll look at a place for maybe an hour, and so I can take 10 pictures, see 100,000 galaxies, and have a reasonable chance of finding one. In here, I have to look at 1,000 square degrees. So I got to look at a 40th of the sky before I have the chance of finding a supernova. So I can't really do it galaxy by galaxy, because there's just not enough galaxies around and they're very faint. I got to look for a half hour or something. And so it's just a technological issue about looking at enough sky in that center bit with a big enough telescope. And the new technology, for example, the Sloan Digital Sky Survey, where a lot of these were discovered, allows you to get into this area now with huge digital cameras that we haven't had in the past. But in 1998, we didn't have the big digital cameras. So we didn't have any of these exploding stars in the middle bit. Just wasn't able to do it. But we have filled it in now.
Okay. Maybe at the back, yeah. Yeah, that student over there.
Thank you, Professor, for a wonderful talk. I've got one question related actually to this plot. We can see that the supernova with the highest redshift is about 1.
Yep.
Is there any supernova that has much higher redshift? Because if we need to study more about cosmology, we might need more, further supernovas. But if we don't have this, what are the alternatives as standard candles? Thank you.
Yep. So the most distant supernovae we have right now that we can measure distances are literally on this diagram. It is very difficult to go further than this with modern technology because the light of the supernovae gets stretched. So we need to observe into the infrared, and we do not have giant arrays on giant telescopes yet in the infrared. James Webb Space Telescope will change that. That will allow us to do it. But at some point, we think these objects probably take 1 billion years or so to form. And so we're probably